Welcome to Oddly Real. I'm Nem Stefanovic. Magnetic fields are a fundamental phenomena of nature. We're familiar with bar magnets, horseshoe magnets, or refrigerator magnets, and the attraction or repulsion to other magnets or surfaces. But what are these magnetic fields? Where do they come from and how do they work? Some of these fields are produced from the properties of matter, such as an inherent magnetic field from elementary particles like electrons. We can also generate magnetic fields from moving charges, like the charges in a current-carrying wire. Additionally, magnetic fields induce a force on moving charged particles. This has the effect of bending current-carrying wires in a magnetic field. Magnetic fields have also been used to engineer electric motors, where magnetic forces are responsible for generating a torque to rotate the motor's rotor to power devices. Furthermore, a solenoid or coiled current-carrying wire is used to produce a strong, uniform magnetic field for energy storage and a variety of other purposes. In this episode, we learn about the fundamental fields and forces of magnetism. Additionally, we look at example situations involving the application of magnetic fields and forces, including devices such as electric motors and solenoids. What is a magnetic field? We define a magnetic field based on the force that it would exert on a particle. The field itself occupies a region in space such that every point in that space defines both a magnitude, the strength of the field, and the direction of the field at that point. Magnetic field strength is measured in units of teslas. Unlike electric fields, which can originate from fundamental charges in nature, like electrons, magnetic fields do not have a magnetic particle of origin. However, certain charged particles do manifest a magnetic field. For example, electrons have a spin, which is a quantum mechanical property, not a literal rotation, which is inherent to the particle, just like mass or charge. The electron spin generates a magnetic field. Additionally, electrons also have orbitals in atoms which also produce magnetic fields in a material. Some materials, like ferromagnetic elements such as iron or nickel, have electron regions where the magnetic fields are aligned to produce stronger fields. It is possible to apply a strong external magnetic field to the material to align these regions together. When the external magnetic field is removed, the material continues to possess a permanent magnetic field. Magnetic fields are also generated by moving charges. If a charged particle possessing charge amount Q moves with a velocity v through a magnetic field B, the particle will feel a force. The magnetic force is directed perpendicularly or to the side of both the travel direction of the particle and the direction of the magnetic field. This means that the magnetic force on a charged particle does not have a component pointing along the forward path of the particle's motion, so it can't change the speed of the particle or its kinetic energy. It can only change the particle's direction of motion. We can visualize a magnetic field by looking at a bar magnet. We draw field lines as a visual aid to help see the magnetic field through space. Note that a real magnetic field permeates the entire region of space and is not made up of actual lines, but this visual helps to understand the field better. The magnetic field lines pass through the body of the magnet in closed loops. The fields originate from the North Pole and loop back through the South Pole. Notice that the field lines are bunched up closer together at the poles, which depicts that the field is stronger there. Opposite poles attract and like poles repel. Our own planet Earth has a magnetic field around it that resembles the fields of a bar magnet. When an external magnetic field is applied to a current-carrying wire, there is an impact to the moving charges within, which results in a phenomenon called the Hall effect. For example, imagine there is a current-carrying wire, meaning there are electrons that are traveling along the length of the wire. Next, we expose the wire to a magnetic field directed from the top of the wire down through it. The moving charges will experience a magnetic force that will push them to the right. In doing so, this produces a charge separation in the wire material where there are excess electrons to the right and a deficiency of electrons to the left. That means there will be excess positive charges from the atomic nuclei that have fewer electrons around them on the left-hand side of the wire. The charge separation across the sides of the wire now results in the creation of an electric field, which exerts an electric force on the moving electrons in opposition to the magnetic force. The electric force builds up to eventually cancel the magnetic force, resulting in an equilibrium of charge separation. The separation of charge results in a potential difference or voltage across the wire, which is measurable. Note that the forces that are produced on the moving electrons in a current-carrying wire from the Hall effect are transmitted to the wire itself. The electrons do not leave the wire, so as they are pushed to the side, the wire itself gets pushed to the side. The force on the wire is proportional to the wire's current and the strength of the magnetic field applied to the wire. When a charged particle moves at a constant velocity v through a constant uniform magnetic field, it experiences a force laterally to its side. Thus, the particle starts to curve. In fact, the curvature will trace out a circle. The radius of the circle can be calculated as the radius r is equal to the mass m times the velocity v of the particle divided by the charge of the particle q divided by b, the strength of the magnetic field. Charged particles can be captured and stored in this way. In fact, charged particles can also be trapped using non-uniform magnetic fields, such as those in a magnetic bottle. In this case, the particles spiral back and forth between the ends of the field where the strength is strong. Notice that the shape of the bottle results in forces directed toward the center of the bottle. In fact, electrons and protons are trapped this way in Earth's Van Allen radiation belts. The particles travel from the north and south poles, bouncing back and forth. Solar flares can disrupt the fields by injecting additional charged particles, which produce electric fields to drive the particles down into the atmosphere. These particles then collide with atoms and molecules in air to emit light and produce aurora. Green color is emitted from oxygen atoms, while pink light emits from nitrogen. Let's look at an application of magnetic fields in the form of an electric motor. The principle behind its operation is that a current-carrying wire experiences a force due to a magnetic field. For example, we can create a magnetic field using two permanent magnets. A current-carrying wire in the form of a loop is placed within the magnetic field. A force is produced on the wire perpendicular to the wire and the magnetic field. Here, the force is directed upward on one side of the loop, while the force is directed downward on the other side. This generates a torque to spin the loop. Notice that there are also lengths of wire at the sides of the loop that produce forces in direct opposition to each other, which don't contribute any torque to the motor rotation. In reality, there is also a commutator on the motor, which is a component that reverses the direction of the current for each half revolution to ensure that the magnetic forces are always pointed in the proper direction to ensure that there is a steady rotation. Typically, a motor would not have one loop, but many loops in the form of a coil to improve the torque. The torque of the motor is proportional to the current in the wire, the area enclosed by the coil, the strength of the magnetic field, and the number of loops in the coil. A current-carrying wire also produces its own magnetic field due to the presence of moving electrons. We can visualize the magnetic field by using field lines in a diagram. Here, the magnetic field lines take the form of concentric circles. The field strength decreases by 1 divided by r as the distance from the wire increases. The strength of the magnetic field is also directly proportional to the size of the current in the wire. Inside the wire, there is also a magnetic field that takes the form of concentric loops. Here, the strength of the field grows in proportion to the radial distance from the center of the wire. At the center, the field is 0, growing outward until it reaches its maximum at the outer edge of the wire. Let's take a look at another example of the application of magnetic fields in a device called a solenoid. A solenoid is just a tightly wound helical coil. Inside the solenoid, the magnetic field is strengthened and the field lines are approximately parallel. The strength of the magnetic field inside the solenoid is proportional to the current in the wire and the number of turns per unit length in the coil. The magnetic field outside of the coil tends to cancel, in the ideal case being 0 or close to it if the length of the coil is much longer than its diameter. Finally, magnetic fields store energy. We look at the example of the solenoid. The energy is stored uniformly throughout the interior of the solenoid since there is little magnetic field outside of it and the magnetic field within the solenoid is uniformly distributed. We can write the magnetic energy density, or energy per unit volume, of the magnetic field at any point within the solenoid as U equals to B squared divided by 2U0. We see that the energy is proportional to the square of the strength of the magnetic field, B. Additionally, this formula is valid for any magnetic field, not just the field in a solenoid. It is also worth mentioning that magnetic fields don't just arise from the motion of charged particles or from the intrinsic properties of elementary particles like electrons. Magnetic fields can be produced from changing electric fields, or vice versa. However, we'll leave those details for another time. I hope you enjoyed watching this episode, and remember, oddly real, really interesting.